we discuss about. Meanwhile, I have to talk to the here. Okay. So damping ratio data is also critical as C over CC. If you have a mass brain damping system, then we can model this like MS double dot. If you give initial condition and then there is no input of force input, right? So then you do the solution like x equal to a in the st, and for x dot you have a and in the st. For x double dot you have a and square in the st. You can plug it in over here. You get this answer like a s square plus e in s plus k a. So you see a is coming everywhere. So you will have this characteristic equation, which is also 3.5-1 in our book. And I taught you this thing last time that if you want to plot it on the Laplace plane or the complex plane, real and imaginary plane, if the roots of the characteristic equation align in the complex plane, then it will have an oscillation there. If you give an initial condition, then it comes down. And on this, if the roots are lying here, and so you don't have any damping. I taught this last time, but if your root is lying on the real axis, then it will look like initial condition is given to the mass and it will stop without oscillating. So suppose over here, if you want to find out, okay, if this is root s two, this is s1. Complex conjugates they always behave like a pair. So or in this case it is negative zeta omega n. One more thing here you can find out, and this is also equal to this is equal to negative zeta omega n. This portion is also equals to 1 over time constant. This is, you know, the division sum. So if I draw the, I don't have the book, I have current based on the book, but if I draw this is the root here, this is angle beta. So the zeta from here can be found by cosine beta. And this is, we talked about this last time. So we can solve one question. It says that 3x double dot plus 21x dot. So compute the time constant and the frequency of oscillation, if any. So if there is any time constant, how would you find it out? And if there are some oscillations, how would you find out the oscillations?
Find the roots of the characteristics equation and find zeta.
Good. Yes, let's find out um, the roots of this characteristic equation. So this is m, this is c, this is k. One more thing, in the standard second order differential, the characteristic equation with the mass spring Laplace system, it is like this. And and from here, you want to find out what are the roots. So can you help your professor tell me the roots? The MATLAB, I'm trying to find out the MATLAB.
-2 -5.
Monster says it is -2 and -5. So e to the st, and if I plug in this one, e to the negative 2t to the negative, I'm not. So this t, if this equals to 1 over 2, this becomes tau, the time constant. This time constant, because the definition of time constant is that the first time constant happens to be like e to the negative 1. That if there is an initial condition given to the mass, this like this mass, if I give initial condition to like 2 centimeter, so if I go 2 centimeter here, then I leave it over here. Since these are the real roots, it will not have oscillations. It will just come back to the mean position, which is the equilibrium. So this is my mean position. We also call it equilibrium or mean position. It does not go down further because of the real roots. If there are real roots, the system will not oscillate about the mean position. And now the first time constant happens at 37%. Let me double check. E to the negative 1. What is exponent? Exponent negative 1. Yes, 37%. 0.37 or so if this is 37% of 2, what is like it just say just 1 for instance, so it is 0.37. If it reaches here, this is the first time constant. This is for the time domain. But the question states, let me read the question. I don't know what there is. So compute the time constant and the frequency of oscillation if this is. So the time constant for this one would be 1/2. You see, this is the first time constant, which is 1/2. And it is dominant. The one which is dominant in the roots, which is near, like negative to negative 5. This is less dominant. If it is away from the origin, it will have less effect on the system. You see, what is 1 over tau 2? This is about 0.2 seconds. And what is 1 over 2, which is 0.5 seconds. So it will last for half a second. This will last for 0.2 of a second. So this is non-dominant pole. It's a non-dominant pole. and the time constant here, which is dominant, it is 0.5. And if you want to find out, you want to find out the what is the 4 times the time constant? So it is zero point 0.5. So zero point 0.5. So after 2 seconds, the system will come to the mean position with these roots, with this mass, with this spring, with this damping coefficient. It will take about 2 seconds to uh, come back to the mean position because 4 times the time constant is the key that it has completed 98% of the mean position, like it has gone through that response. You see my point? Either if it is a step function, for example, if I give the mass a step value, so over here, rather than the initial condition, if I apply the force of a certain value, so it will go up and it will reach, since these are the roots, which are the real roots, so it will not oscillate. Some graph will oscillate about the step value. Suppose step value is 1 Newton for a force. So the 37%, that point on the on the x-axis will give you the first time constant. You see my point, guys? So this is how you will solve this question that was asked in the classroom, how to find the time constant of the second order differential equation. Now I want to do the second question here, or the third question here, 2x double dot. This is 3.44 part C. 2x double dot plus 8x dot plus 58x. So can you guys help me online or in class? What are the two roots for this case?
-2 plus and minus 5i.
Negative 2 plus minus 5. Ah, that's good. So this imaginary portion, or we can write down as the general formula is plus minus iota omega d. So this is the imaginary part, which is omega d. The real part is zeta omega n. Is the negative side. So I would not. This is not the problem. This is not the actually. The roots are here. These are the complex roots, and this is the minus zeta omega n. So I will say this portion is a dominant time constant 1/2 seconds. It's just the one uh, real number because for both roots it's a complex conjugate, so the real number is not changing, so it will damp out its oscillate. And if I give initial condition to the mass like 2 centimeter here, it will start coming back, it will go up, it will oscillate, and the envelope in which it oscillates, it is it is zero and D. And the oscillations, like for example, here to here, this is, I'm sorry, this is period. I will say time period of the time oscillations. And this is omega d. So this is oscillation. This is your answer. Omega d is 5 radians per second. Do you guys understand how to find out the time constant now? Second order.
This problem asks for the um, frequency of oscillation.
Yeah.
Correct. Is that not omega n?
Now the question is, when you see the damper involved, this is omega t. When it is spring involved, this is omega n. Okay. The question was asked if it is omega n or if it is omega. This is omega n, and the relationship. You see the relationship between omega d and omega t equals to omega n. This is just the formula which you don't have to learn by heart, but you can just write it down like. There is one more question asked by this one of the students. So, question is problem 3.31. Use the determine the natural frequency of this. It's like a pendulum attached with a lever system. Fulcrum is on the pivot ends. So how will you solve this question?
Rayleigh's method?
Good. So let's do the Rayleigh's method. So I'm gonna use this lever principle. Like if you see a fulcrum is here and this is the length and this is like a x1 and this is length and 2, this is like a x2. So the product over here, product on the other side. So I can find out the relations. For example, if I know the x2, I can find out x1 from here, L2 over L1 times x2. So let's apply the same thing over here. Suppose this is my x2 and this product d2, d2, okay. So the deflection in the spring would be x2
We get x1 is L1 over L2.
L1 over L2.
Yeah,
How?
if you consider those like similar triangles, the ratio of L2 over x2 equals the ratio of L1 over x1.
Oh, there is my mistake. You see, you are taking a similar triangle, like over here. Oh, I'm sorry. This should have been. This is L1. Yes. Ratio of this side L2 over L1 equals to X2 on X1. These are the two similar triangles. So you're right. This I was thinking S equals to R theta. Theta equals to theta theta. Something like this equals to 2. Yeah, you are right. So I mixed up something. So theta is constant. So X1 over L1 equals to 4 L2. Correct? The same thing. So maybe I think you are right. Sorry, I was confused over there. I mixed up. So this is correct. So with this, if we use this portion like over here, so if this deflects to the right, this deflects downward, so we can use the same principle like two ratios d2 over x2 equals d1 over x. For this x1. So the deflection in the spring x2 would be equal to d2 over d1 times x1. And for maximum displacement, we know that we assume that displacement is a sine omega t. And for maximum displacement, it is a, correct? So I can write this down here. I can write this down like x2 x2 equals to times a, correct? And we know that the formula for the Rayleigh equation is T max minus T min. So if we assume that equilibrium position is at datum line, so this is 0, and this also stops. This goes to 0. So T max equals to V max. So V is the potential energy and T is the kinetic energy, is half m V square or x dot. If you take the x1 dot here, so let me show you over here. X dot is the velocity. This is cosine. So we have to take the maximum value over here. So I can write this down half omega n, and that is equal to the deflection for this one is spring is x2 equal to d2 over d1. So I can write down half k the deflection d2 over d1 times a square. And that is the V max. And we have to equate it with the T max according to the Rayleigh's equation. So if I equate it, half m omega n a square is cancelled by a square is cancelled by a square, half is cancelled by half. So if we do the math, the natural frequency comes out to be d2 over d1. Okay. This is how you find it. Any questions, ladies and gentlemen?
You could also find it in terms of theta as well, though, right?
Right, you're right, exactly. I tried, once again, he said we can use the similar triangles, but we can find out through the theta, which is constant for both sides. Theta is same.
That's the same answer I got. But my question that I had was, how come we don't take when you're looking at the pendulum equation or example, we took the potential energy of the movement. How come in this one we don't? Because doesn't potential energy of the mass change as it moves up and down?
Oh, that's a good question. So what happens that the potential energy, even if you take that one, it will balance out. And let me show you what happens that if you have a spring and you attach the mass with this, so it starts deflecting. So this weight equals to the a times the deflection, static deflection. So in the V max, this is a V max. We have to consider the due to gravity and due to the strain energy due to the spring. We have to consider two potential functions, and the gravity is the potential energy which is minus mg. Since it goes down, you see it goes down to so from the data line, if the particle of if the or if the mass goes down below the datum, it loses potential energy. That's why we have to subtract from there if it stretches, and we have to add it into over here half k x max plus I believe x square delta k delta. Oh, sorry, not k, just the delta. Yes. So this delta for the max. So even if you, at the end of the day, you will see that the mass gravity will be cancelled out with k delta. So even if you take, and usually in the oscillations, we can assume that the data line is considered to be the zero, so you don't need to worry about taking the mg term in it. But if, as in the pendulum, as the questions asked, Professor, what is the case of pendulum? In the pendulum, it is not the case that we are considering it's not oscillating, or it is oscillating, but it is we have to consider weight as an option over there and solve the problem in the pendulum case.
All right, thank you.
So that now I have tried my best to completely explain the review. The review problem, I would say, go to the lecture, and I'm going to upload. I've already uploaded 4 lectures on the YouTube, and the previous go over to the lecture and homework problems and the textbook. Review the textbook. That way you will get grade A. I think it's not difficult. You will have 3 questions, 70 minutes time. I would increase the time for you to 90 minutes. Usually in class, I give 70 minutes to solve 3 questions. So since online students, maybe I can increase to 70 to 80 minutes. So let's go to the next chapter now. What do you mean by harmonic response? Like a simple harmonic motion. So if you have suppose a mass, okay, the mass has the output. Suppose output is x and input is f, and f is the harmonic means like sine omega t. For example, if you are giving some kind of input function, correct? Sine omega t or amplitude is a sine omega t. So let me write down a sine omega t over here, for example, over here. So this is a single frequency given to them. Sometimes a force to which is the second harmonic, a to sine. And sometimes you are giving multiple frequencies at the same time, like to see some sweep signals. Sweep signals mean that starting initial frequency and the ending frequency, and then you have the time in which this will spread out. Okay, so let's discuss each harmonic, single harmonic once time. So the transfer function, I would say TF means transfer function is the output over input. And what is that transfer function? I'll teach you in a bit, but let me tell you that if you have a sine omega, the input function, how about the output function? How it looks like, you will see it has a different amplitude. This mass will start oscillating at a different amplitude, but remember, harmonic will not change. If it is being oscillated at single harmonic, it will have a different amplitude, but the harmonic will not change, but the phase will change. Okay, phase will change. What I mean by that, let me show you the difference. This is the conceptual part. Suppose if you have a graph sine wave, suppose this is my sine wave. Okay, guys. So the output function maybe it may be looking like different. You see this part. So this is my output. This is my input. So this in this chapter we will learn how to find out the output response for sine wave, for multiple sine waves, to find out the bandwidth. Bandwidth is a term used at which we have the the ratio or the response is maximum. We will learn about the bandwidth in which the system responses about equal to resonance. So what is the bandwidth for very high amplitude? Like we say, like low uh, low pass filter, high pass filter. Mean high frequency contents can pass through this transfer function. Low frequency contents can pass through this transfer or band frequency. So we will learn that in this chapter. So let me show you the formula. This table 4.1. When you go home, you will read this table. What it says, like if I suppose if I if I show you the same let me show you the same diagram here. So now in this case we are not we are not having an initial condition, but we are having, let me show you, we are having some kind of force input. So if I model this, look, how would I model this mathematically? You will use the Newton's second law. And the right hand side is this is plus sign. let me rewrite here. This is plus sign. Right hand side will be the input force. Okay, and input force in the form of a sine wave is written like this. So you will consider the right hand side as well. And for this, you can find out the same thing like the roots. What are the roots of this? So S equal to R plus minus QI. And finally, you will see let me show you something over here. There are two things. If you closely look, this is kind of not purely starting from zero at the same slope. So this is called, we call this as a transient response. Another name is natural response. And this is after it settles, after the transient response vanishes. You see, the force is being supplied continuously for a limit or whatever time we force is being, so then this becomes a steady state response. You see my point, guys? The steady state response lasts as long as the harmonic is given. When I will teach you, so you are the graduate, I usually teach the control theory lab where we perform the sweep signal to the mass and to find out zeta value and find out where is the maximum response at what is the resonance. So you can see the mass will start moving. Maybe I can show you, or I can share with you that video. How can you see the maximum frequency, maximum amplitude when you give a sweep signal? So my question is, so if I write down the steady state response formula, so what is that formula? So let me show you. The formula for steady state response is this one, and I can write down here. This is x of x dependent by time. It is depending on the frequency. What is the magnitude? The magnitude of the amplitude or the amplitude. It is given as f naught over and this is the amplitude of the steady state response. Okay, this is how you will find the amplitude. Usually you will be given this function in the question. I will solve one question for you in a moment. And the phase angle, how would you find out this phase angle, which is also depending upon the frequency harmonic. So how would you tangent inverse? Tangent inverse. Let me show you. The tangent inverse, the denominator is C omega. Okay, guys, now the question is, how will you find out the phi? It will be in the third quadrant. Is it in the third quadrant? If this angle is in third quadrant, if this ratio is, if this is positive, you see, this thing is k minus omega square. How would it be in the third quadrant? This angle, how would it be in the third quadrant? Let me tell you. If the denominator is positive, So actually, I tell you, this is the iota axis, this is the real axis. And the phase angle is tangent inverse C omega divided by K minus M omega square. You see where did I get? This is the in the denominator. And you see, if you want to find out the angle of our transfer function or angle of this transfer function, the numerator is the angle of the is a real number. What is the angle of a real number? Let me show you. The angle, suppose the pole is located here, the angle is 0. The angle of real number is 0, correct? But for this case, in the denominator, this is not 0. Why? Because C omega is, so you will write on negative tangent inverse C omega over K minus A minus M omega square. A negative goes here inside, so it becomes negative. Everything negative is in the denominator for the j-axis. J-axis above the x-axis is all positive. The third, either if you see this denominator, if this is negative, then where is uh, the pole line? In the third quadrant. You see my point? If negative c is in the denominator, this is the third quadrant. Why the third quadrant? Because if I say to you that this, if this denominator is negative, so negative, the real part is negative, the denominator is negative, where is the phase angle line? It is lying in the third quadrant. And the book has confused some students. It happened in the last semester. They were confused. They changed this position. You see, it is k minus omega, k minus m omega square inside the formula. But they changed the position because they say when you have a negative term, then you make it positive. But I just want to teach you from the formula that if you see the negative, or if you replace it in the book says that m omega square. Let me show you. If you write down like this is the same thing add like this. You see, you agree with me? If you take negative sign outside and flip their terms, okay, you same thing. So if this is positive and then multiply by negative, you will still get the negative number. You see my point? So the book has explained in a complicated way that they change their places with the without showing the negative sign to the students. So I'm telling you that you don't have to change the position of m omega square k. You just have to do the math. But the book says that if you do this m omega square minus k, if this is positive, then the quadrant is third quadrant. The phase is line is in the third quadrant. And if m omega square minus k is negative, it is lying in the fourth quadrant. You see my point, guys? So what if this is negative? If this is negative, means negative. The negative here, multiply by negative here, so you get positive, positive real axis. So it's the same thing. You guys understand? Let's do one problem. We still have about 20 minutes, so let's do one problem. Then you can understand more clearly. Let's do, I want to start from the example first. Let's start from the example 4.1-1. The question is, the equation is given. Then x double dot plus 70x plus 100x equals to force function. And the force function is harmonic signal of this value. 307 is the amplitude, 40. So remember, this is omega, which we also call the oscillating frequency. So I can write here omega equals to 4 radians per second. And what is this? This is amplitude. Usually we write down amplitude with sub f. You see my point? With sub f naught. So I can write here 307, maybe Newton or milli. We don't know, but it's arbitrary. So now what you have to do here, find the roots. Find roots of the equation without the right hand side as to be forced. So what are the roots for this one? Can you help your professor? What are the roots of 10s squared plus 70s plus 100?
-2, -5.
One student says s1 equals to -2. So now these are the two roots. So I can write down the response with a -2t. Another root has a response -5. So this the transient response will contain these terms, and they will disappear. Now I can ask you, what is the time constant for this function? You will say, Professor, this is 1/2, and for this is 1/5, because you have to make this time equals to tau such that the answer is e to the -1. You see my point? So that way, so this is non-dominant pole, this is dominant pole. So it means the system will stay under transient influence up until 0.5 seconds. Then it becomes steady state. So now the question is find the steady state response. Find the. So you have to find out the steady state response, this one. And that is equal to x x formula is this one, f naught over. Let's do this math together. This is 307, agreed. So let's write down 307 here. Now another parenthesis, the bracket k. Let me write down m. This is m equals to. So let me write down the equation 10 x double dot. This is 100. Sorry, this is 100. So here m equals to 10. So k equals to 100. M equals to 10. Omega equals to. Now I will go back to see. This one is omega, correct? So I can write down omega equals to 4 radians. So I can write down 4 here whole square, okay? Plus c omega. C is 70, omega is 4 whole square. Can you help your professor find out the magnitude? Open your calculator. You should get about 1.072 amplitude. But you can verify.
Correct.
One student has verified, and in the class you guys have verified. Yes. Okay. Now let's find out what is omega. So in omega, if I go back to this, yes, this. Let me grab this formula, and this formula. Let me grab this one over here. Now I want to do the math here. 1, 2, 3. So this is in radians. So let's do this. Tangent inverse. C is 70, omega is 4. K is 100 and M is 10. 4 squared. What do you guys get for this one?
1.36.
1.36. So 1.36. Now you will tell me where is the which quadrant is it lying? This is either in the third or in the fourth. You will help your professor which quadrant this phase is the angle is lying.
The third?
Third, good job. Let me ask you, is it negative? The denominator term I did not calculate it. Is it negative?
I think it's negative.
Yes, it is negative. And how about this? I already told you that if the denominator is in the denominator, then the numerator has a negative automatically there. You see, because you have to take the things from the denominator and the numerator. You remember, if you flip, then you have to negative sign. So it is lying in the third quadrant. So if it is 1.36 radians, you have to add pi into this. To take the from positive real x, we usually take the angle from the 0 radians plus pi. The answer is 4.5 radians. So the final answer for this one is you just plug it in over here. So x of t equals to 1.072 sine 4t plus 4.5. Let me block this out so it is not confused. Have you guys understood? Can you solve such question in your homework problems? So usually the question is, I'll give you a forcing function. You will find out the response x of t. Sometimes I will ask you the transient response and add this responding to. Transient response you have been doing in the previous chapters. Like over here, if I show you the transient response, it is negative e to the negative 2 plus e to the negative sorry, 0.5. So when you go home, you solve this problem on your own. Okay, now let's solve another concept. Let's go to the another concept. Then we will solve problem with a new concept. This is we call as the magnitude ratio. You change this color here. Okay, now I want to show you if you have a mass spring damper system, then you can write down this magnitude ratio. What is the magnitude? Suppose this is the mass, other than the C and omega involved in it. Although they are over there, but just see. So if you give the forcing function like F naught sine omega t, and x is the output, which is frequency dependent. So magnitude ratio is the output response divided by the input. And if you take a look over here, look the previous chapter, previous page. What is this? If I want to find out the magnitude ratio, you just divide the amplitudes. Output amplitude divided by the input amplitude. And what is left on the right hand side? This term, look, 1 over, let me write down, this is equal to, so magnitude ratio equals to x over f naught, x, this is f naught, okay, equals 1 over so this is equation number 4.1-17. So any let me show you one thing. If you have a complex number, lying over here, and you can represent this complex number by the magnitude of this vector. Let me redraw it here. This is, suppose this is a point, a pole, and this is the real axis, this is the imaginary axis, and it has the angle P. And this the magnitude of this vector actually it should be the magnitude of this vector, it should be on the right hand side, is the scalar value of this vector. Okay, that is a scalar value. If I want to represent this vector in terms of exponentially, so you will see this is a scalar value. Remember the scalar value, because the vector can be completely represented by the scalar value and the angle p. You see, you can represent any vector in the real and imaginary plane. This is how you represent the vector. But if I want to write down, angle can also be written in terms of e to the iota p. This is another way to represent an angle. So can I write down the same the vector, which is iota omega equals the magnitude ratio e to the iota p, which is also the dependent upon the frequency. If the frequency is higher, it will be different than the frequency is smaller, which will be different. Have you studied Bode plot before? The Bode plot is usually like the dB value and the phase value. So if you have a Bode plot, sometimes it goes up, sometimes it goes down. Have you studied this frequency function starting from the zero frequency of DC contents to the resonance? This is the resonance, okay? When you see the larger bump, that is the highest dB value where the frequencies, at that frequency, the mass will be oscillating at a very, very high amplitude. So the highest peak in the dB or the magnitude value gives you the resonance. You might have studied in your undergraduate course, or if not, I can make a small video about the Bode plot. Do you want me to make a small video? I can share with you. And then for this one, and there is an angle. Usually when you have a resonance, the angle changes from maybe from 90 to maybe 90. 90 to negative 180. So I'll share with you this one once the time comes. I will share. So let's do another problem. So how would you give the in MATLAB? How will you plot a transfer function? Suppose this is my mass and this is my output. This is my input. If I say you what is the transfer function, you will say, Professor, this is x over f. That is equal to 1 over ms squared. This is mass spring damper system. It has a spring damper which is not shown, but second order. So then you can, if I say this is 5 x cube, x double dot 3x dot plus 9 x equals to f. So you can use the transfer function is output over f equals to 1 over, and then you can, this is known as the characteristic equation. And if the roots, they will tell you the behavior. But right now I want to show you how would you model in MATLAB. In MATLAB, there is a function known as TF. Okay. And if I want to plot this transfer function, suppose this is letter G, estimate. So how would you plot it? Numerator, the transfer function, numerator coefficient, denominator coefficient. This is numerator. Numerator can be written like just a single um, one, correct? So I can write here 1. The denominator, the coefficients of this characteristic equation, starting from the highest degree. What is the coefficient of s square? 5. Coefficient of s 3. Coefficient of s or constant, it is 9. So if you plug in MATLAB TF like this, you should get the transfer function. And if I ask you, what is the phase angle of this transfer? You remember I told you that if there is a pole here, and that can be completely represented by the phase angle as well as the magnitude. I told you this vector equals to m p or m e to the I p. It's the same thing. Okay, guys, this is a complete representation of a vector. So if I say to you, okay, this is the transfer function. Now what you have to do, you have to replace this transfer function into the frequency domain. How will you replace this into frequency domain? Let me show you. You just replace s by s omega. S by I omega. Replace s by iota omega. So now this s is the Laplace domain. Now it is in the frequency domain. Can I write it like this? K minus m omega square. Can I write it like this? Correct? Do you agree with your professor? And the magnitude, do you know it's the imaginary number? And imaginary numbers are orthogonal to each other. The real is here, imaginary is here. The pole is the real number and imagine they are ortho at 90 degrees. So the magnitude would be equal to 1 over, this is the magnitude formula, real square plus imaginary square. You see that? This is the same you have been doing before for the right angle triangle. So this and the same thing has been written in our book over here. So I can write here the magnitude in this form k minus m omega square whole square plus c omega whole square. This is the magnitude, but how will you write down the phase angle? So let me show you. The phase angle can be written down like the transfer function of the what is the angle? You see, sorry, this is the you can write down here. This is the how we write out this phase angle. So the way you will write it down here, the in the numerator you see it is 1, in the denominator it is 4 m. So I can write down here in the numerator what is the angle of a numerator angle, and then negative whatever you see. You will show me like this. And what is the angle of a real number? I just told you earlier. So the real number, the vector is lying here. It's 0. Agreed? And and the angle for this one can be found by tangent inverse and omega c omega in the numerator and k minus m omega square. And if you want to rewrite here, negative is multiplied by c, so I can rewrite here tangent inverse c omega over m omega square minus k. So this is how you will find out the phase angle of the transfer function. So I will share with you some homework problem and we will go from here next time. Thank you guys.
Are you going to release homework 4 today?
Yeah. Yeah.
Thank you.